All right, so it reads, a battery of electromotive force EMF 12 volts and negligible internal resistance is connected to a network of 2 lamps and 2 resistors as shown in figure 6.1. I would say that as you all try to find practice problems to, sort of test yourself to see how well you've mastered these learning outcomes, at this stage, look for questions where this is true, negligible internal resistance. Don't try to solve anything yet where you have internal resistance. There'll be like a little resistor here near the EMF and usually a dashed line sort of around it. Anything like that, we'll sort of eventually be able to deal with it, not quite yet. So, computer screen is frozen. Sorry about that. Come on there. There we go. All right. So negligible internal resistance, like you read up here. So try to find questions like this, until we cover sort of next week, we'll cover internal resistance and non-ohmic components. I know we already talked about a filament lamp as being an example, one of those, a diode. All right, and so it sort of explains that the 2 lamps here have equal resistances. The 2 resistors have resistances R and 28 ohms. They're connected at a junction X. The resistors are connected at junction Y. The current in the battery is 0.5 amp, that's given here, and the current in the lamps is 0.2. We want to first calculate the resistance of each lamp, and there is a way to sort of do it first, in other words, one calculation leads to the next, but if you preview sort of the next thing that you're going to have to do here, it's calculate the resistance of this resistor R. And I think the way that I solved it first was like I figured that out first, and then I figured out, sort of what were the resistances of these. But if they give you this calculation first, then there should be a way to do it without that. In other words, it's possible to solve it without first calculating R. So what would that way look like? Between this point and this point, there's 12 volts of potential difference, right? Like the voltage drop across this is equal to here. That's Kirchhoff's, a consequence of Kirchhoff's second law. We talked about in a parallel circuit, like this branch is in parallel to this branch right here, right? Once the current gets to this point, there's a node where the currents diverge there. And so these lamps are in series with each other, but in parallel to these resistors over here, right? So I do have a parallel circuit like this. The voltage drop across this point and this point is all 12 volts. So I can kind of think about it like, if I want to know the value R for the resistor, and it's V over I, and I know that between here and here, all 12 volts is going to drop, and I know the current sort of through this branch is 0.2 amps. What's 12 divided by 0.2? That would give me 60 ohms of resistance sort of in this branch right here. And remember the way that we add resistors that are in series. In other words, this is in series with this, right? Like there's one path from like the electrons to go through from here through X to here. And so I can kind of think about, well, that combined resistance is R1 plus R2, but they have equal resistances. And so it's really like, well, this R 60 ohms is equal to twice the resistance of my lamp. And so the resistance of each lamp must be 30 ohms. Okay, so you can get to that kind of 30 ohms by just considering sort of the 12 volt drop from here to here. The other way to sort of solve it, and the way that I sort of initially approached it, was kind of like the first thing I calculated was what is the total resistance in this entire circuit. I said, okay, R equals V over I. I'm conveniently given the total voltage and the total current, like the current in the battery. So by taking the ratio V to I here, 12 volts to 0.5 amp, we're getting the equivalent resistance in this entire circuit. Okay, in other words, this arrangement of resistors draws 0.5 amp of current from this EMF because the total resistance in the circuit is 24 ohms, right? Because that's just 12 divided by 0.5. So if I know that there's a 0.5 amp, I know what the equivalent resistance is in the entire circuit, 24. And then I kind of honed in on this. I'm given this value of resistance, and so R equals V over I.
Teachers, please excuse the interruption. This is Mr. Fry. We were going to have PERT testing and again at 11:30 today, but due to connectivity issues, we have decided to cancel that for today. All students who have signed up for PERT, please make sure you are checking your school email addresses for dates and times of any testing. Once again, PERT testing today is canceled. We will reschedule. If you signed up, be sure to check your school email for dates and times of testing.
You can take a look on my YouTube channel and see how often I'm interrupted in the midst of a calculation by messages just like that. All right, so V equals IR, and we know that R is 28 ohms. Well, what's the current that's going through this? So if all 0.5 amps hit here, we know 0.2 amps are going this way, so 0.3 got to be going this way, right? So we know that we got 0.3 amps times 28 ohms to get the voltage drop across this guy right here. So what's 0.3 times 28? Everybody with a calculator knows it's 8.4. Or everybody with good mental math abilities also knows that. All right, so it's 8.4 volts dropping across this resistor. And remember, all 12 volts drop from here to here, right? So they drop across this branch and across this branch. And so 8.4 dropping here, how many are dropping there? 12 minus 8.4. I heard somebody say 3.6. So if there is a 3.6 volt drop across this resistor, then I could apply Ohm's law there and say, what's the value of this resistor R? R equals V over I, the voltage drop across it. We calculated 3.6 volts, the current 0.3 amps, right? Because 0.3 are going this way, 0.2 are going that way. And so R equals V over I, 3.6 volts divided by 0.3 amps gives us a resistance of 12 ohms for this resistor right here. And so they tell us this one's 28. We just calculated this one is 12 ohms. Now that's what they ask us in part 2, actually. They ask us what is the resistance of, this in part 2. So I'm just telling you that there's more than one path to the solution. So you don't have to solve the 30 ohms this way. I actually solved like, well, what's this one? Once I knew this one's 12 and this one's 28, coupled with this information, I can solve for the 30 ohms of resistance that way. Question?
Could you also done it where you, what I did was I took the 12 volts, divided it by the 0.3 of the full resistance, and then knowing 28, I took that resistance and subtracted that.
You did the 12 divided by 0.3 to get the total voltage drop across
Yeah,
this.
total voltage drop, and then I subtracted the 28 to get 12 volts.
So yeah, very similar to sort of how we approached it on this side, right? Like doing this calculation over here, you could do the same thing. You could say all 12 volts drop across this branch too, and rather than dividing by the 0.2 amps, you know that there's 0.3, so you calculated like we did here, 60 ohms dropping across this side. You got the total, what was it, 40?
Yeah.
Because 28 plus 12, so you said 12 divided by 0.3 is 40 ohms of total resistance across this branch, and the same way that I summed them to realize 30 plus 30 is 60 over here, you could do 28 plus what equals 40, and it's got to be 12. So yeah, that's yet, it's sort of using this strategy, but on this parallel branch to solve for this resistor R. But I was still sort of going through what's another way to get to this answer here. All right. So this is saying if I know the total resistance in this circuit is 24, and these are parallel branches, then it's kind of like this. 1 over 24 equals 1 over, now it would be whatever the combined resistance of sort of that branch is. And if I know that they're identical lamps, then I can just sort of assign a variable to them for their resistance, like I'll call it. It's like what I'm solving for in part 1 there. So I'll call it R1. So because those two lamps are in series with each other, I would add them to get their total resistance along that path, along that branch. But once I've combined them that way, I have to remember that I'm summing the reciprocal, right, with the reciprocal of this combined resistance to get the 1 over 24. So it's like I'm adding R1, well, let me kind of put it like this. What is the combined resistance just of this? if this is R1 and this is the same R1, then the total resistance across here would be R1 plus R1 or 2R1, right? Like that would be the total resistance across here. The way I need to add it though, with the resistance of these guys is the reciprocals, right? So it's 1 over 2R1 plus the same thing for this one. If this is 12 and this is 28, then the combined resistance across this guy here is 40. So it's 1 over 40 plus 1 over twice whatever these resistors are equals 124. At this point, you could try to do some sort of fraction magic or something like that. I just do it in a calculator and just turn it all into decimals. And so 1 divided by 24, you get like 0.0416 repeating equals 1 over 2 R1, where this is the R that I'm solving for. Like I know it's 30 because I already solved it, but it should work this way too, right? And then 1 divided by 40, 0.025. If I then subtract 0.025 from both sides, I get 0.016 repeating equals 1 over 2 R1. Then I can multiply both sides by 2, R1, divide both sides by this. So then I'd have the inverse of this quantity equal to 2R1. And so if 2R1 equals 60, then R equals 30 again. And so this is a more roundabout way to get to the solution, the same 30 ohms that you get here. But you're calculating a lot more along the way, like the total resistance in the circuit, for this information, and then sort of practicing both formula, right? Because you have to use the resistors in series because each of these is in series sort of with each other, yet in parallel with this other set of resistors, right? And so how do you approach that mathematically? You see what we did is we collapsed down the combined resistance of the two resistors in series into one value, 2R1, 40. We collapse down those values into one single value that we can then combine the way we do for sets of resistors in parallel. That's a complex circuit because these are in series with each other, as these are in series with each other, and yet they are in parallel, like the resistors R and 28 are in parallel with these lamps. Okay, so it's a tougher circuit to sort of consider, but the answer to this one is 30 any way you calculate it. Okay. And so we already solved for this resistance R. Remember that the resistance of the lamps was 30, the resistance R here was 12. And the way that we solved that was considering the voltage drop across the 28 ohm resistor with 0.3 amps going through it, gave us 8.4 volts. And so 12 minus the 8.4, right? The EMF equals the sum of the PDs. And so if the EMF is 12, then the voltage, the potential differences have to add up to that. And so if 8.4 is dropping across the 28 ohm resistor, then we can calculate that the potential difference across my resistor R equals, I should say it like this. The voltage across resistor R was 3.6 volts, okay? And then we can calculate its R equals V over I by taking that 3.6 volts over 0.3 amps. And that's how we get the law. And again, there was another way that we could solve that too. Determine the potential difference V sub xy between points x and y. So for this one, we really have to sort of consider it carefully. we want the potential difference between sort of those junctions, they call it, the junctions X and Y. What's the potential difference between this point and that point? If the potential drop across this entire sort of these nodes here is 12 volts, right? Like 12 volts is dropping from here to here. Okay. How many volts drop across this one? How many volts drop across this one? Well, this one we've already calculated, right? We said if this one was 8.4, then this one was 3.6, right? Was that right?
Yeah.
Yeah. So if there's 3.6 volts dropping across here, this is a 30 ohm resistor with 0.2 amps, then V equals IR over here. And we've got our 0.2 amps times our 30 ohm resistance in the lamp. There's 6 volts dropping across this lamp. And so if 6 volts is dropped from here to here, but only 3.6 volts is dropped from here to here, what's the difference between these points now? In other words, there's 12 to get from here to here, and I've dropped 6 of them on this side, but I've only dropped 3.6 of them on this side. So it's the difference between those values. Okay, that's the potential difference between X. In other words, if I were to connect a resistor like this, and it's already a complicated enough circuit, like why put more resistors in it? But if I were to do it, there would be a potential difference between those points as well, right? Equal to whatever that is. 2.4 volts. There's a potential difference of 2.4 volts between X and Y. So even though I don't have anything connected between those, right, there is a potential difference between them. So 2.4 volts there. Get that answer where it belongs. Right there. Okay, 2.4 volts. Now we want the total power dissipated by the lamp and the total power produced by the battery. The total power dissipated by the lamps, I calculate like I squared R, but I've got, 2 of them. So the current in each lamp, each 30 ohm resistor is 0.2, right? And there's 2 of them. So it's like 2 times the 0.2 squared times 30 over the power produced by the battery is I times V is, I think, the easiest way to calculate that, because we're given sort of the 12 volts, we're given the 0.5 amps, right? The battery has 0.5 amps drawn from it total. So the calculation is 2 times 0.2 squared times 30 over 0.5 times 12. That should get us there. 0.2 amps squared times 30 times 2 means that the power dissipated by the lamps was 2.4 watts. And the total power, half of 12 is 6. And so 2.4 watts divided by 6 watts is a ratio of 0.4. And lastly, state and explain the effect, if any, of the change of replacing the resistor R with one that is lower. So the resistor of resistance R is now replaced by another resistor of lower resistance. State and explain the effect, if any, of this change on the ratio that we just calculated. So we just calculated the ratio to be 0.4. Now, what's going to change if we make, that R there lower? So let's just remind ourselves that we had 12 volts, and then they went over some resistor R over here that was 12, but now we're going to make it like 6 or 10 or something less than that, right? And then it went kind of like this, and then went across some lamps over here. All right. So instead of, and this was 28. And so instead of having 12, it's gonna be like 6 now, give yourself some numbers to work with if it's easier. This is really the part of the circuit that concerns us. All right, we know that there's 12 volts EMF over here. All right. if all of a sudden this thing becomes lower resistance, does it change anything happening to these lamps over here? It doesn't, right? The voltage across them is the same. There's still 30 ohms of resistance. And so the power dissipated by the lamps is constant, it's unchanged, right? It does not affect it. The fact that there's less resistance here will not make these any brighter, dimmer, nothing, okay? There's still the same voltage across them, still 12 volts, still 30 ohms of resistance, okay? If there's negligible internal resistance, which we are considering for this problem, we'll see the effects of like, oh, internal resistance in a battery, that affects the whole circuit really, okay? But in this one, we can consider those effects to be negligible. Now, the total power produced by the battery, that is going to change, okay? That will be different, but how will it be different? And so if you put less resistance in a circuit, just think about it almost intuitively. If there's less resistance in a circuit, what happens to the charge that's being drawn from the battery? All of a sudden, there's less resistance, and so it's going to do what? Pull more charge. Okay, more charge, more current, more amps of current will be drawn from the battery. That doesn't mean any more amps are going to go through this branch, right? Because that's not fixed, right? There's still 12 volts, there's still 30 ohms of resistance. It means that, okay, now there's going to be more amps going through this branch, right? Because there's less resistance there. So you decrease the resistance in the total circuit. Remember, it was 24 ohms, right? The total circuit resistance was 24. Well, now it's something less than that, which means it's going to draw more amps of current, okay? Because it's the same voltage, and now the circuit, resistance has decreased, something less than 24, right? In this case, it's more. We don't have to calculate it, we just know it's going to be less. The total power produced by the battery is going to do what? Going to increase because we calculated I times V. So if we draw more current from the battery, then the power produced by the battery increases, right? If you put a bunch of resistors in parallel, you're decreasing the overall circuit resistance, right? Something, 20, 18, it keeps getting less and less. And so you're drawing more and more current from the battery. When you do that, the battery is producing more and more power. Does this mean we found some sort of unlimited supply of energy here? Oh, here's what you do, just keep adding resistors in parallel. The battery will produce ever more power until what? Until you drain it, okay? In other words, you will drain that battery a lot quicker if you just keep putting a bunch of things in parallel to it. Well, these lamps are just as bright as the ones before. If I keep adding lamps in parallel, they're just as bright. Why? Because there's the same voltage across them, there's the same resistance. But your battery is going to be dead a lot sooner because you've got 20 lamps in parallel, okay? So every lamp will be just as bright. If you put them all in series, you'd see, that they're not going to shine so bright because the current is the same everywhere there. The voltage stays the same across every parallel branch. So what effect will that have if the numerator stays constant but the denominator increases? So you want to state the effect first of all, okay? The ratio decreases, right? Because the denominator increases, and so the ratio itself decreases. Ratio decreases because, right? Don't forget this part and explain, all right? But I always state it first. I don't want, sometimes you start with the explanation. Because the circuit resistance decreases, more current will be drawn from the battery, therefore more power is produced by the battery, therefore the ratio decreases. You can't say it that way, nothing is wrong with that, like starting with the because this is true, this will happen. But I prefer that you do it in the order it says, state first and then explain. So kind of go through that thinking, get to your answer and go, okay, the ratio decreases because, and then say all that. The ratio decreases because less circuit resistance draws more current from the battery, and more current from the battery means more power is produced by the battery because it's calculated I times V, right? So if I goes up, then the power goes up right along with it. This is then a worked example from question paper 23 from October, November 2019 question.